This is Jack Jackson. In this video, we're going to continue our look at limits, and we're going to see how we would modify the definition of a limit to account for one-sided limits. So let's start with limits from the left. So the formal definition of a left-sided limit, it turns out to be exactly the same as the formal definition of a full-sided limit, except right here, this part right here is changed. In the full limit, this would go, x would be from c minus delta up to c plus delta, but x is not c. And here we have it less than strictly on the left side of c, from c minus delta to c. Here is the another way to write that here, or we could write it this way. Okay, and but notice that the condition on y, on f of x, is not changed. It's exactly the same as in the regular limits. So now we can see that if we look at something here, and we're trying to look at our little rectangle here, notice that as we move delta, it only goes to the left of the point, and then it comes in closer and closer as we put a smaller value of delta until we get this part inside the rectangle. Notice this time we're not concerned with what happens on the right side of x equals c, which is given by this vertical line. Remember, before our box went both sides, equal distance both sides horizontally of this orange line at x equals c. Now it only goes to the left. Okay, so that's the difference there. And of course, then a right limit, this is the full limit. See, the box goes on both sides, coming in closer and closer. And the right limit, here it is, as we move delta, it's coming in closer and closer this way, but only from the right side. So again, pretty simple thing. The proofs and everything work basically the same way. It's just that you restrict the x values a little bit more for the left to be between c minus delta and c, and the condition on y is the same. From the right, we want our x to be between c and c plus delta, and then the condition on the y is the same. Okay, and so that is the same way. Now, let's also look at what happens when we have vertical asymptotes. And of course, we know what does that mean when we say, for example, that the limit as x approaches c from the left of f of x is infinity. Now remember, this doesn't mean the limit exists. It's a more descriptive way of saying how and why it does not exist. And of course, when we can say that, we would say infinity there, not just does not exist, even though in some sense both are correct answers. Just like when we have a figure that's a square and I say, what shape is it? You would say square rather than saying, oh, say rectangle or quadrilateral, which are also true answers. The square is the more descriptive answer. And so the same way would go here. When we can say appropriately infinity, we will say that. So what does it take formally to say that the limit is infinity? Okay, so what this says is for real numbers c and l in a function f, we say the limit as x approaches c from the left side of f of x is infinity if and only if for every positive number m greater than 0, there exists a real number delta greater than 0, such that if x is on the left side, this is a left limit, so x is between c minus delta and c, then f of x is big. Bigger, how big? Bigger than m. Again, this does not imply that the limit exists, but rather describes how the limit does not exist. And in this case, we say the line x equals c is a vertical asymptote of the function. Okay, and there's a right-hand version of this, and the only thing we change is we change this condition right here to be x greater than c and less than c plus delta, so we're going on the right side. Now to get the full limit as x approaches c of f of x to equal infinity, to say that, which means, of course, it doesn't mean that actually the limit exists again, it just means it's growing without bound, really is what it means. Then we have to be able to say both the left and right limits are infinity. So let's look at this, let's look at an example here. So in this example, we're going to look at 1 over x minus 3 squared, and we're going to show that as x goes to 3, this goes to infinity. Okay, so let's look at this Geogebra sketch here. So if we're looking at the right limit, we're concerned with this stuff to the right. And so notice that here we can pick a value of m. And we say, okay, I think, the limit's not bigger than m. So again, it's like a challenge. So rather than giving an epsilon for a challenge, we give a value for m. And here we say, oh, well, that's no problem. As long as I pick, now if I pick a delta, say, that's in here, say, then notice that when you go on the right side, look at the pink rectangle, there's nothing in that. So there's no function values below that. All are above that pink rectangle in that interval right there. So all of the y values, see, they go from about here on up on the right side. Similarly, so that would tell us that we have picked an appropriate delta for that value of m. Well, what if we pick a bigger value for m? Let's say we go up here. Well, now that delta no longer works because you see there's some of the graph in the pink rectangle. Some of the graph is below m for that choice of delta. But what do? Oh, that's no problem. We just make a smaller delta. So if we bring it in a little smaller, we can get that in so that all the y values are above that. And so since we can do this for any value we pick for m, no matter how high we make m, we can go in small enough so that all the y values are above that. Then, in fact, we say that the limit from the right of this function as x approaches 3 is infinity. Similarly, we just look at the green rectangle, and again, if we start, doesn't matter where we start, let's say we start here. Some of this graph is in the green rectangle, so we do not have an appropriate delta. We need a smaller one. Get a little bit smaller delta, and now all of the graph is outside of the green rectangle, so if we take x's in here between c minus delta and c, all the y values here are up, looks like they're from about here up. They're all definitely above that value for m. And we make m a little higher, we need to bring this delta in a little smaller. And again, we see all the y values are above that if we're between these two vertical lines at c minus delta and c, so the limit from the left is infinity. Or if we look at the whole thing as one big rectangle and look at all the x's between c minus delta and c plus delta, if all the y's are above that, then the full limit will be infinity. Okay. Now, what about limits that approach negative infinity? Okay, well, it's the same thing, except now the value of m is a negative number. I think I can use the same sketch. Let's see here. Now we just let m be a negative number, and what we want, of course, this one's going towards positive infinity. But what we would want is we would want all the y values to be not only nothing in here, the y values would need to be below this m. And see here they're above, so that's no good. We need it below there. But I think if I just modify this function by, like, say, put a negative here, that should flip it upside down. And now this function is going to negative infinity as x approaches 3. And so that point is, no matter how low we make it way down here, then we can choose a small enough delta to get all of the y values to be below that horizontal line. And so that would be what we mean by negative infinity as the limit, which is not really a limit again, it's just saying how it does not exist. So for real numbers c and l and a function f, we say the limit of f of x as x approaches c from the left is negative infinity if and only if for every real number m less than 0 there exists a real number delta greater than 0, such that if c is less than x, which is less than, let's see, this is from the, let's say this is from the right, then try this again. So it approaches from the right. If x is greater than c but less than c plus delta, then f of x has to be greater than that m. F of x is less than that m, which is some negative number. So it's just going further and further down. Okay, and that's the right-sided limit. To make it the left-sided limit, we only change this part right here to this part right here. C minus delta is less than x is less than c. And for the full limit, then both the left and right limits both go to negative infinity to get the full limit. Or you could say it this way, c minus delta is less than x is less than c plus delta, but x is not c. And then that would take the whole thing directly to here. Okay, in the next video we're going to look at how we can formalize limits as x goes to infinity or negative infinity.